I'm sure you're all suitably refreshed after that excellent lunch, and welcome back to this continuation of the session on modelling and prediction. We have a couple of very experienced speakers to follow. Our first presentation will be by Professor Rob Melchers, who I think is one of the finest corrosion engineering researchers in this country, and his topic will be modelling durability of reinforced concrete structures. Now, Rob is Professor of Civil Engineering at the University of Newcastle. Until recently, he was concurrently an Australian Research Council DORA Research Fellow, and prior to that, Australian Research Council Professorial Fellow. He holds a Bachelor of Engineering and a Master of Engineering Science from Monash University, and I heard him talking to Brian Cherry this morning, saying one of the first people he met as an undergraduate out at Monash was in fact Brian. Rob also has a PhD from University of Cambridge, and he's a Fellow of the Australian Academy of Technological Sciences and Engineering. He's also an Honorary Fellow of the Institution of Engineers Australia. His most recent awards have been the 2009 ACA Corrosion Medal, the 2012 J.S. Chung Award, and the 2013 John Connell Gold Medal from the Institution of Engineers Australia. In 2014, he was eminent speaker for the College of Structural Engineers, the Institution of Engineers Australia. So will you please welcome Rob Melchers.
Thank you, Bruce, and thank you, organisers, for inviting me to come and say a few words in honour of Brian. As Bruce has already mentioned, I first met Brian when he was brand new at Monash and I was a brand new research student, and he came walking in there and I could hear him coming, and I thought, this guy's from Cambridge. It was kind of scary. Okay, I'm a structural engineer by background, and I'll later on explain to you why I'm actually looking at this. But let's talk a little bit about what I'm going to talk about. I want to talk a little bit about the background, why we're actually doing this, some observations from real reinforced concrete structures, not just experimental work, a brief rehash of just a few experimental aspects which have already been covered in a sense by previous speakers, but they're important. Then I want to focus on two areas: the initiation of reinforcement corrosion, and I want to separate that from active corrosion, and Warren's already told you about that a couple of times, I think, this morning. And then say something about concrete cracking, because I think that's an area that we have kind of overlooked, and I think it's really important. Then the model, if you like, which is extremely simple, and then some practical implications. So let's talk about why we do things. Structural engineers are concerned with the safety of physical infrastructure, buildings, bridges, you name it. There's a whole host of them, as you can see there. And if we get it wrong, in some countries I'll get shot, in other countries I might go to jail or get a heavy fine. So it's not a picnic. We've got to get it right. And increasingly, we're talking about the lifetime management of structures. It used to be once you just build it and forget it, and someone else many, many years later picks up the dregs of what you've built, what's left over. Increasingly that's changing, and increasingly there's now emphasis on, can we predict at the start, when we even are designing the structure, how long it's going to last and what we have to do to make it last a long time. What do we mean by a long time? For most structures, buildings, bridges and so on, maybe 100 years is the maximum. But if you get into that business about nuclear waste containers, for example, you're talking an awful long time. And I don't know how we're going to predict that, but fortunately I don't have to worry about that. But we do talk to some of the nuclear corrosion people, particularly in Europe, who are very much worried about those sort of lifetimes. The main materials, as we've already been pointed out, are reinforced and pre-stretched concrete and structural steels. I'm not going to say anything about structural steels, but they sit in there as an important component. We've heard a lot about CP of various sorts and coatings, and that's great. But I remember some years ago having a couple of days with a senior bridge engineer from another state, and we looked at lots of bridges, mainly reinforced concrete bridges, and he said, oh, these have got cathodic protection on them. We don't know anything about it anymore. The systems don't work anymore. It's all deteriorated and we don't know what to do. If only we didn't have to have this stuff. Which is an interesting sidelight, I think. I think the point was mentioned, you have to maintain the CP systems and the paint coatings, and if you don't do that, you're going to have problems. So I'm going to talk about systems that don't have those. So, our question is how safe? Not only just how safe is it now, but how much longer will it last, and that requires, obviously, prediction. Whoop, what happened? I can say anyone can predict, but at what accuracy? And what we don't want is hocus pocus. And there's an awful lot of people out there who are selling a hocus pocus. I think some of you all know what I'm talking about. Engineers rely mainly on quantitative models. That's in broad terms. Structural engineers in particular. They are based on what we currently understand, and they are calibrated to real information. Information that we get from the field and from past experience. Sometimes from the laboratory, but the field experience is really important. And there's a long and successful history, certainly in structural engineering, of doing that. And it also includes that the models get upgraded as time goes by. So we learn from previous experience, say the old models have got to be upgraded in some way. And that's relevant, I think, to what I'm going to say today. The models for loads, for strengths, when we first build the thing, and for fatigue and so on are pretty well understood, but the models for deterioration on the whole are rather bad. They're not very well developed at all. And corrosion is one of those, and I'm going to talk only in corrosion in marine environments. And typically the corrosion literature will give you things like, oh, it's very corrosive, or it's medium corrosive, or not corrosive. Well, I'm sorry guys, that's not good enough for us. We need to be much more specific. And also you get things like, well, this is better than that, that's better than something else. That's also not good enough. We need to be able to do better. So, quantitative prediction. Reinforcement corrosion. As we've heard, is a major issue still. I didn't know what anybody else was going to say. But we can reduce it. Oh, I know what's happening here. Am I turning the thing off? Their own deterioration mechanisms, I've mentioned that already. Research approaches. How can we actually look at corrosion behaviour? We can do it in a laboratory, and typically that implies relatively short-term experiments. You know, a year or 2 or 3 or whatever. That's already a long time. And if you think about most PhD programs, they run for 3 years, so you can't design a program that runs for more than about 2.5 years because you've got to give the poor devil time to write up. Then you have to ask the question, how relevant are those results in terms of practice if we're talking about 50 or 100 years for the real structure? We can accelerate them. We can apply currents, for example, to the reinforcing. And then the question is, how valid is this? I've got some bars sitting in my office, reinforcing bars. One lot came out of a real structure that had been exposed in the 1930s and was dug out of the concrete, I don't know, about 10 years or so ago. And I've got another couple of bars that were in a reinforced concrete slab that one of my colleagues tested in our laboratory with impressed current. And you just feel the surfaces and they're completely different. And you think, on that basis alone, what can we say about accelerated testing? It's dubious. The other thing that's often done, and you've heard a lot about this, is electrochemical testing, but you've got to remember, you've got to put it in context. And if you look up some good books like Scully and Kelly's book, for example, and some other works, you'll see they are actually surrogates for the real thing, and they have to be interpreted. Now, you can't interpret them if you don't know what the actual behaviour is. So there is a problem. The other approach, and which is the one that we're really following, is what we might call an archaeological type of investigation, where we're going to look at real structures, existing structures, particularly ones that have survived for a long time, and then say, what can we learn from that? Now, the only problem with that is we've got to reconstruct the context, the period of time over which this thing survived, if you like. What actually happened to it in its whole life up until the point that we look at it. And that, of course, has some issues, but fortunately for most of the things we look at, we can pretty well say, well, it's more or less the same as it is now, unless we know that there's been a major change of use or something like that. But for many structures, they have more or less the same environment as when they started. Forget climate change for a minute, huh? So that's our approach. Now, one of the problems with that is, typically, is sample size. Because you can, if you look at just one structure, you say, well, that's what happened to this thing. But if there's something slightly different about it, would we have got a different result? And fortunately, we have been able to find just a few cases where we have big sample sizes. The accepted conventional width. Let's talk a bit about background now, because we need to get that in. The life of the structure depends on the rate of ingress of aggressive chloride, so the reinforcement, or the rate of carbonation. You've heard about this before. The professional opinion is reduce in with diffusion, use dense concretes with high cover, use additives perhaps. I'm not going to talk about that at all, to reduce pore spaces. I'm not going to disagree with any of this, but what I'm going to focus on is why. Sorry, something seems to be going on. I seem to be pressing the wrong button. Despite this, so we know all this, and yet, if you look around, there are lots of concrete structures that haven't survived for very long, maybe 20, 30 years, and then they're in bad state. So there's something we're doing that doesn't guarantee long-term behaviour necessarily. But if you look around some more, there are some structures that have lasted a long time, and I'll give you some examples of that. In quite severe environments, and I think we need to understand why those have lasted such a long time. Now, in the paper that you've got, there is a different example to the two examples I'll give you, just so that we have a broader case, and there are lots of other examples in some of the papers I refer to, because we have systematically gone through a lot of structures. I'll just give you two, including our most recent one. This is the Hornibrook Bridge that was built in 1935, just north of the city of Brisbane. I think it's in a suburb called Redlands, something like that. It's called the Hornibrook Bridge because it was built by a supervising engineer and financed, I understand, by Hornibrook, Sir Emmanuel Hornibrook, who has a well-deserved reputation, at least in structural engineering in this country. It's 2.7 kilometres long. It's on Bramble Bay there. It's right next to the Pacific Ocean. The Pacific Ocean's on the other side. There's quite a large tidal range. At low tide, the bottom of all those piles that you can see there, you can see the sand. So there's a big tidal range, and this is supposedly the worst exposure environment that you can have for reinforced concrete. It was demolished in, as I said, 2010-11, basically because the superstructure was a timber road bridge, and it was already totally inadequate, too small, and all that sort of stuff, and for political reasons they decided to pull the thing down. Now, we were alerted to that by an engineer in Brisbane, and he said, come and have a look at this. The piles they're pulling out are fantastic. There's no sign at all of corrosion. So this is 80 years. The crossheads, they weren't quite so good. And you can see here, if I can find the right button to press. Yep. These are the reinforced concrete beams on the approach spans. So these are three piles, the crossheads. Crossheads aren't too bad. The piles here, the beams here are not terribly great. But then we look at the piles, and there's virtually nothing wrong with them. Now, it doesn't say so on the slides, it doesn't say so on your notes, but Warren reminded me before to why is there a difference. And the big difference is that the piles are Class A concrete. They've got much more cement than the rest of the structure. The crossheads and the approach beams, they're Class B concrete. So they have lower cement content. I'm just going to focus on the piles. There are nearly 900 of them. And this is just a snapshot that I took when I visited the demolition yard over there. You'd be hard-pressed to find anything that's got anything wrong with it. They're all in fantastic condition, and these were in a tidal zone, remember? So the question is why? What's going on there? So we were able to persuade the department up there to let us have some random samples. They just selected the piles and sent them off to the University of Newcastle for us to look at in detail, which we did. Now, this is just a typical example. You can see the concrete on the left-hand side, a cross-section of the piles. They were just cut with our massive concrete saw. igneous rock, or virtually no sign of reinforcement of corrosion anywhere. There's a little tiny spot at the bottom where one of the ligatures has got a little bit of corrosion. The other thing that's noticeable is that all the pHs on the surface here are all around 12. Now this is after 80 years, right? The concrete chloride levels were way above threshold level. Way above. Doesn't matter where you look, it's above a threshold level. I think the normal threshold level is about here somewhere in here, in this range. Yep. And the bars are about there. The concrete was extremely hard. Our lab guys got them to dig out some of the bars, as you can see down the bottom there. They busted the bits on the jackhammer. The concrete was 60 MPa or so. Okay. The bars that were recovered showed either no corrosion at all, they were like the day they were put in, or they had a little bit of rust that was basically, as Warren mentioned earlier, like green rusts. Now, green rusts, you've got to remember, only come about when you have virtually no oxygen. So that means that there was virtually no oxygen in that area at all. However, and I'll come back to this case later, one of the piles, when it was being pulled out of the ground by the demolition contractor, showed something that they didn't expect. And he said to me, oh, come and have a look at some photos I've got in my office. And I thought, oh yeah, this could be interesting. But these are the photographs. What he found is that when the pile was being pulled out, it had actually kinked. And that is the area of kinking. And now have a look what's happened here. And this relates to some of the things that Jack's been talking about as well. That's the cross section. Two of the bars, I've got to be careful what I'm looking at. Two of the bars have been flame cut. This side here is rust staining. This is where the concrete was fractured. And here you can see, well, the bars basically disappeared. So on that side, that bar and that bar were basically like this. Nearly all the steel had gone. Now the first question is you ask, well, how did this come about? The next question is, where did the steel go? There was no rust. Just a bit of water stain, just a bit of rusty stain. There was no rust on the outside. Because when we inspected those after we isolated them in the demolition yard, just to make absolutely sure, so there has to be a mechanism for getting rid of the rust. And then we looked at it a bit more from a structural engineering perspective. We decided, how did this thing is cracked a long time ago. Could it have been cracked during installation? In other words, was it bent because they were cast lateral this way? Because you could tell because one side was rougher. And if you then look at it, it would have been lifted up and it had cracked, and the crack had been there all those 80 years. And during that time, this happened. Actually, the case that started me on this whole business, because many years ago I decided I wasn't going to get involved with reinforced concrete, corrosion, just stick to steel and seawater, was this case here. If you ever go to Arbroath on the east coast of Scotland, there's a little place called Arbroath where they have smokies, which is smoked fish, and I happened to walk along a coastal path there for one Sunday afternoon because my wife had gone home already. She left me in Scotland, and what else do you do on a Sunday afternoon in Scotland except go for a walk along the coast? And I came across this thing. We now know it's, at the time we did all the investigation, it was 65 years old. The seawater washes over it in the winter time. There's a lot of rain obviously over there. It was constructed during the Second World War. It's about 1.6 kilometres long. It would have been low-level technology, and the bits of interest are the handrails. You can just see them in there. I think I've got another picture of them. Yeah, these handrails. Those bits in there. They were all precast because the verticals were cast later and you can actually see it from the construction. But there's nearly 1,000 of these. Now out of that 1,000, we discovered that some of them had cracked really, really badly. And that was about 10% of the whole lot. But when we inspected the concrete and talked to the local council and so on, we found that these were replacements for the 1943 ones. So 90% of the 1943 ones were still there. It's the ones that had failed that were built later as replacements. And then you have to ask yourself, what's so special about the 1943 ones? So we did that. You can see the size, roughly cover. I mean, this is really high quality construction, man. Look at the size of the aggregate. Look at the cover. And this is just a random sample that someone else had cut. So it wasn't exactly high quality concrete. And when we looked more closely, what did we find? Seashells in the aggregate, in the concrete. That tells us pretty well that they just used the local seashells, this local sand, and mixed it with seawater, so it was full of chlorides right from the beginning. And yet, it lasted 60 odd years. We know that seawater was banned in the 1960s, but it does tell us there's a high calcium carbonate content in that concrete. And that that sort of worried me. So we looked more closely at these samples. These are just some random samples. 1943 concretes on this side. And if you look at the pHs, you'll find this cracking and therefore reinforcement corrosion only when the pH is around 8.5 to 9. The bars that are in higher pH concrete, there's no evidence that we could see of reinforcement corrosion. There may have been some microscopic amount of corrosion, but let's not worry, nothing to cause any problems. At one time, we had some samples, fortunately, that the local council is allowed to take out of those handrails and take back to the lab to the University of Dundee and later on elsewhere. And one day we were breaking up one of the samples that were left over, and I must say I got the shock of my life. He was one of those handrails, and here should have been a bar, and there wasn't. There was nothing left. If we go back further along in this direction, this is what the end of the reinforcement looked like. And I thought, what's going on here? And if you look more closely, sometimes you saw this, but the important thing is that always occurred where there was a crack in the concrete. And of course that ties in with the picture I showed you before, and I think Jack's shown a few times already. So again, the question is, where does steel go, how and why, and we'll come back to that. So out of that came the question of, well, we need to rethink, because I looked at the current literature at the time, which I sort of understood, I thought, this doesn't make any sense. These cases don't fit what the textbooks tell us. And the model you've heard a lot about already is the so-called Tutti model. That goes initiation time and then corrosion starts. And the more we looked at lots of examples, which I'm cutting through a whole lot of work here, months and months and months of literature survey that I'll come back to in a minute, we decided in the end there's something funny about the way it works. We get initiation, small amount of corrosion will occur. This is corrosion loss, if you like, or damage, whatever. Doesn't matter. No, not damage, corrosion loss. Damage is different. And then nothing much happens. And then only later on do you get this active corrosion. Now, we proposed that in 2006 on the basis of the information we then had. And we argued that the mechanisms involved in the early stages, that's this initiation period, and this here, were actually completely different. Now, if you think about it, if the concrete's really bad, it's possible that it just goes straight up here. But I want to talk about good quality concretes, and I'll come back to that. So the classical Tutti model, or whatever you want to call it, is too simple and so on. And we had this notion that, the most likely thing is that somehow the chlorides, in particular sodium chloride, increases dissolution of the alkalis in the concrete. Now, there was a little bit in the corrosion literature to tell us that this was a possibility, but we had no evidence. So we just put it out there and said, this is what we think is happening. And the paper got published anyway, so must have been all right. Now, I also mentioned we did a massive study of the literature. We just went through report after report after report. And for structures in the United States, this was really good because they would tell you what type of aggregate was used in a particular state to build whatever bridges that were available. It's much more difficult to do in the UK or for Australian bridges. We don't have too much limestone in this country anyway that's used, but in the United States there was a lot of limestone used. And on that side, I've got the results for igneous aggregates. So we've got here chloride content, and this is pretty fuzzy. I mean, there's a fair bit of fuzziness in that result, but that was our best estimate. And also the two times that I've got here, the time when we thought initiation occurred, typically from the reading from reports when they first saw signs of some sort of rust staining or something like that, to say that, yeah, something's going on. But there was no significant damage to the structure. And then later on, they reported, in later reports, that something serious was going on. Now, these numbers are somewhat rubbery. I'll be the first to admit this is for igneous aggregates. And what I've already taken out of these is the cases where there was alkali aggregate reaction, because that, if you read the original paper, that's in there, and there's a difference. So we said, no, that's another mechanism, we don't want to know about that, so that's out. So if you read the original paper here, you'll find there's also reference to alkali aggregate reactions, and I've taken those out. If you look at the cases where they used dolomites, or non-reactive dolomites, and calcium carbonate or limestones, both of these times go up quite a bit. And of course, in retrospect, that makes sense because we've actually added more alkalis to the solution. But I was very, very worried, and I wrote a paper about this quite a few years ago, saying, what's going on here? Calcium carbonate is supposed to be bad, some people tell us, but it's actually a bit more complicated. Note that the conventional chloride threshold values are those grey bars that are up there, and we're talking about a lot more chloride than that. Taking stock, so what have we got? Observations from real structures tell us significant reinforcement corrosion only when the pH is less than 9 or thereabouts. Minor low oxygen rusts on some bars even after decades of exposure. Some concretes still have very high pH after decades of exposure. Why? Very high chloride levels do not always cause corrosion. That's what we can deduce from those cases. Again, why? More questions. Oh, gee, I'm sorry. Now, some texts talk about pH less than 11 causes corrosion. And you think, well, hang on, what's going on? That doesn't quite fit this scenario, but we'll come to that. And calcareous aggregates appear to increase both of those times, and we have to ask why, and I've sort of foreshadowed that already. And severe, very localised corrosion is observed in some concretes, right? And again, why? So, the way we thought about it was, well, reinforcement corrosion isn't all that different from any other corrosion, it's just that the environment's different. So, the same sort of rules must apply. It's not somehow special. And there are some aspects that I think sometimes we forget. The key factor is the environment. Initiation of corrosion can only occur when those thermodynamic requirements, Poor-Bay diagram and so on, are satisfied. And that tells you, as we've already been told this morning, it's only when corrosion is possible, not the rate. And that's the bit that really is important for us. And in pure water, in natural wet conditions, it requires pH less than 9. Now that implies that somehow or other we've got to get rid of some of the alkalinity. Otherwise nothing will happen, except when we have chlorides present, we can have pitting. And you can read about that in Poor-Bay's 1970 paper. So there's a difference. Pitting versus overall corrosion loss. And even in new concretes, we know that pH is around 13. It is possible, according to the Poor-Bay's 1970 paper, to have pitting, but you need oxygen. And of course you need high chloride concentrations. If one of those is missing, then it doesn't happen. Progression of corrosion. Now, this is the other bit that's important. In pure water, in concretes around the steel, the pore waters are stagnant. And it's sometimes forgotten that it was shown already many years ago that in those conditions the chlorides play virtually no role at all in the corrosion process. And that was shown more than 100 years ago by these two guys in Germany, and it's a nice German paper, you can have fun reading it, and they look at lots and lots of salts, made almost no difference, provided it was stagnant. And why is that? Well, if you go and read Evans's book, even things like carbon steels form a very weak passive layer, right? And he showed that. You can read his book, how he did that. And Dora Brasher in 1967 threw some light on this and said it's only, the chlorides are only important in non-stagnant conditions. because then you actually damage that oxide layer. And if you look at Mercer and Lombard's, I think, a very nice paper published in the British Corrosion Journal before it changed its name, showed that very clearly, that if they used rotating electrodes so they could control it from zero rotation, and then it didn't matter what the chloride content was, nothing much happened. But as soon as they increased the angular rotation of the coupon, the amount of corrosion went up. So they were destroying, if you like, the oxide layer. So the stagnant conditions are really important. Now, as Warren has already mentioned to you, most laboratory experiments don't actually use stagnant conditions, right? So yeah, it's a bit of a problem. So coming back to this now, what can we say about the initiation bit and the active corrosion time? I want to really focus on those. We need to think about what's going on in those periods of time. So initiation, our approach is experimental. We did a long-term experiment where we had very small specimens, 40 by 40 by 160 millimetres with a central bar. We put them in high accuracy steel forms. They were all made exactly the same way. We used seawater to make the to start them off. Range of water cement contents, aggregate cement ratios, fog room, all that sort of stuff. And that actually means that we can rule out carbonation as an issue. And then every year initially we broke open 2 samples to have a look, and we saw nothing for these things. Except after a little while we saw pitting along one side of the bar, if I can call it a side. And it was the bottom of the bar, away from the casting direction. So we had them like this, we cast on top, the bar was through here, corrosion was on the bottom. And when we looked more closely, show you some pickies. Oh dear, I've done it again. I'm doing it again. Sorry. You can see it there. This is just one photograph of it, and there's heaps and heaps. I can show you lots more. And they are pitting. And then you've seen a picture a bit like that before. If we then looked at the pitting, it was next to the air voids in the concrete. So the passivation bit wasn't there. And you can see another picture here in the middle showing, this is the separated bit, but here's the air voids, and that's where the corrosion was on the bar. And here's another picture showing the loss along, there's a cross section here. And we now know that, of course, that this also happens in practice. There are air voids present. The voids are correlated with pitting. And the question is, how do the air voids get there? In our case, because we had all these different ranges of concretes, some were quite permeable or porous, if you like, and others weren't. In the porous concretes, we got bigger gaps between the steel and the concrete, right? So there was more pitting, and that's exactly what we saw. And this is still with concrete around 12, pH of 12, yeah. And nothing really changed. We saw that when we first broke them open after about 2 years to the most recent ones that we've broken open at 10 years, and now we're looking at year 13. We see exactly the same, nothing much changes. So what does that tell us? That changes that in that curve, a bit of corrosion occurred and nothing much happened along for the next 10 years or so. Oh, gee, I'm sorry. So what we're proposing is that something like this happens. You have an air void. This is all concrete around here. And at that region, so in the air void sits wetness, because all these samples are quite wet. And so oxygen and water, even if the oxygen is dissolved in the water, it's still oxygen there. And you get differential aeration to start with here, and that happens on this side as well, and eventually it corrodes into here, and all the rusts eventually end up around here somewhere. But the point is that this air void supplies a limited amount of oxygen. And when that oxygen runs out, things all stop. Except if you've got really poor quality concrete, then you get oxygen diffusing in from the outside. And a lot of the experiments, if you look at them, have actually been done with not very good quality concrete in the labs. And if you read the paper, I'll give you some examples of that. Yeah, I've talked about that. Yeah. So you can get longitudinal cracking, and we're now seeing in our worst concretes in our lab, we now see after 13 years in the worst, lousiest concrete, very porous concrete, we're seeing a longitudinal crack. So we've now got to the stage where things are getting serious. But there are other issues. So that gets us, if you like, to this earlier stage here, to here. Now in our lab we didn't have this initiation period because we put the chlorides in to begin with. We just saw this and we saw that. I now want to talk about what happens in here. What causes that to occur? Because it doesn't quite make sense. There's something else has to happen. So the same experiments were used, but we also used one other lot that was made with sulfate resisting cement. Now that came about because someone, when we started these experiments, said you ought to try sulfate resisting cement. It's supposed to have some good properties. And I thought, why not? We'll try that as well. And it's fortuitous that we did, because we ended up, as I'll show you, seeing some things that we probably would have missed completely if we hadn't used this cement. So we used the same type of models, continual exposure of fog room. We looked at it every year approximately, and we looked at the way they were broken open, and we photographed them, and we again didn't see much for many years. But for some it was worse than others. Now this is a typical example. So this is concrete made with sulfate resisting cement. Notice the dark grey interior. And when I first saw this I thought, I don't understand this. I just didn't understand it at all. We had only the samples made with this cement showed this behaviour. All the others just seemed to be grey on the inside. And we had this lighter colour on the outside. I thought, what's going on here? And then we did discover after a little while that the grey, dark grey material was less for the lousiest concretes, the poorest concretes. And that then said, hang on, there's something going on. There's some diffusion process going on. And, you know, it takes a while to get your head around what you're looking at. But it turns out, we eventually found that sulfate resisting cement has a dark colour because of iron sulfides and magnesium sulfides in the concrete mix, and they change to a light colour on exposure to the atmosphere. And that's known, you can look that up, but these concretes hadn't been exposed to the atmosphere. Right? This is just after the thing was broken open. So you have to ask yourself, what's going on here? Well, when I say they haven't been exposed to the atmosphere, that's actually not quite right, but we'll come to it. So what's going on? So we looked at that. So here's a nice comparison. Dense concretes on the left-hand side, the one similar to the one I just showed you. Really permeable concretes on the right-hand side. And you can see there's no dark grey material. We then went and looked at the pHs, and you'll see this is the one on the right-hand side got pH down to about 9 or so, and the bar is corroded. The one on the left, there's virtually no corrosion, the pH is still around 11, 12, something like that. We then started to look at what is actually inside the concrete. And we did that by various techniques, including XRD and EDS and so on. And to cut the whole story short, the ones on the left still had a lot of calcium hydroxide in the mix. They were still quite alkaline. And they would have been because of the pHs. And the ones on the left, there was virtually no calcium hydroxide left. So there was no alkalinity anymore to keep the bars passive. So then you say, well, how did that come about? And then you think, the only mechanism that's possible, let me go back. The only mechanism that's possible is that the alkalis leach out. And then you ask yourself, is that really the mechanism that's causing it? Because ultimately, when all the alkalis have leached out, then you've lost your alkalinity and the bar can corrode. Yep, I'll get there, Bruce. Now we saw the same. When we then realised that, we looked at the other concretes, and this is just one example. Much more difficult to see, but if you look at the pHs, you can see that even for in an advanced state, the pH is still above 9 in the middle and no corrosion of the bar. These are cross-sections cut with a saw, and the pH on the outside is a lot lower. And if you look at the very outside of the bars, we often saw calcium carbonate formed there, and that's what you would expect. So, difference between the light and dark concretes. Dark on the left side, light on the right. You can see the light-coloured concrete shows channels. It's much more porous than... So this was the same concrete mix, same sample, but just out of the dark part and the light part. And if you're under the microscope, you see the same sort of thing. So what has actually happened is that oxygen was able to diffuse into that mix and change the colour. If we then look at the depth of the light-coloured concretes between the Series B, which is the ones I've been describing to you, for Portland cement, and also that's sulfate-resisting cement is the red ones. The B ones are the Portland cement, and K is some samples we made with fresh water. And let's just talk about this side only. This is Smith-Hammer readings, which is a surrogate for permeability, if you like. So these are high strength, low permeability, and high permeability there. The depth of penetration of that light zone is much greater for the high permeability concretes compared to the low permeability concretes. And for fresh water, well, it's not much is happening. For the B series, which is a standard Portland cement mix up here, sulfate resisting cement actually aren't all that great, as we now can see, but it did unlock, if you like, the reason for what we're seeing. So the porous concretes, greater rate of loss of alkali, and of course it doesn't help because the internal exposure, if you think about porosity, the internal exposure of the alkalis will be greater if the concrete is more porous. So it's a dissolution of the alkalis, that's the important bit. And that we know is increased by sodium chloride. Okay, that's probably all I need to say about the overall thing, except a few signs of warning. We saw these. What's going on here? We've got to remember that all the studies on which the current codes are based for crack sizes are based on very short-term exposure experiments. If you go back and look at Beebe's work and so on, it was all short-term stuff. And they were talking about a relatively small amount of cracks. But what we're talking about is long-term exposures and cracks that go all the way and past the reinforcement. And then you think about the scenario I've just painted. We now have a crack through there that allows dissolution of the hydroxides in the cracked area and eventually allows much faster initiation and therefore active corrosion of the bar. The only other question that arises, damaging, okay. So I'm saying the code people need to have a rethink about this. The only other question that arises, which isn't actually in the presentation, is where did the steel go? And if you go back and look at the fundamentals, we've got chlorides, iron, a little bit of oxygen. There's not much oxygen you can get in here, presumably. And ferrous chloride can form under these conditions. And ferrous chloride is one of only two corrosion products. The other one is ferric chloride, which is soluble. So they can flow out in watery conditions. All the other rust products can't do that. They settle out. And for example, when I walk along the coast in Newcastle, there's a post planted in some concrete, and you look there and there's this brown rust stain. Now you've got to ask yourself, how can that brown rust stain ever arise there? It has to have been a fluid material that then became solid, because otherwise you can't get, the ordinary rust wouldn't be able to flow around and settle, they're not soluble. So ferrous chloride plays an extremely important role in all of this. And I haven't got time to go into that. Okay, how do we then think about lifetime prediction? Really, we don't care about this bit. We care about that time here. And that time now, in my view, is governed by dissolution of the alkalis in the end. And that's sped up by chlorides. So we just need to focus on that bit. Now, we can use the results we've got so far, and they're for completely uncracked specimens, and I keep reminding you of that. We can use that to make an estimate. And what do we get? Well, from the data we've got from our laboratory experiments, and remember, these are laboratory experiments under perfect conditions, it's about 160 years for the sort of cracking that we would get for the Hornibrook Bridge piers. Now, they've already lasted 80 years, So we're in the right ballpark. We haven't quite got there, but remember, these things are all perfect, not completely perfect concretes. They're pretty good, but not perfect. Okay, so what have we got? We've demonstrated initiation. There's a little practical relevance in the normal sort of sense. It fits in with what we see. The most important practical parameter is this active corrosion time. And what you get, I would argue that what Carmen was talking about is a bonus. If you can get a few extra years of life out of it, that's fine, but this is really the important part. Once this has happened, you know you're in dangerous territory. Cracking, I've only talked about transverse cracking. I haven't talked about longitudinal cracking because we don't really see that in any of those cases we've talked about unless you've got really poor quality concretes, right? Then you get a different problem. Then the initiation leads to longitudinal cracking if it's a lousy concrete. The deep cracks permit inward transport of, I've just mentioned it, chlorides and oxygen and out leaching of alkalis. Now, I think the important thing is that, in a way, if you start to look at the implications of what I've been talking about, it actually fits virtually everything we see in practice, and it kind of fits the fundamentals of corrosion science as well. So, we haven't relied on any of these surrogate techniques, but we do have some areas where we need to do some more work. We need to refine really how to estimate that time of active corrosion. All we've got is the initial results, which have only been published in the ACA conference so far and the European Corrosion Conference. The alkalinity of concrete versus cements and other alkalis, and we've already hinted at you that if we have lots of other alkalis like calcium carbonate, things are actually better off. But I'm not advocating replacement of cement by calcium carbonate, mind you. Not yet, anyway. The control of the internal surface area for alkali dissolution is important. The rate of chloride-driven alkali dissolution, how that changes, because there's only one solid piece of evidence for that going back to the 1930s, which you can read about in the paper. So there's quite a lot of work to be done that's now coming out of the way we're thinking about it. But the nice part about this, if you like, from an overall perspective, is it gives us a sense of unity between carbonation-driven corrosion and chloride-induced corrosion. Fundamentally, it's the same underlying mechanism. It's the loss of alkalinity which causes the problem. Now, look, I've said all that. I'm going to skip over that because I'm running out of time. Yeah, I've got to thank the Australian Research Council. They keep paying me to do things I like to do, which is good. And they've got a nice bunch of guys already. Toril Pape's been mentioned. Igor has been working with me for the last few years and did a lot of that XRD, EDS type of analysis that I can't do. Dick van der Molen, who used to live in Melbourne for a long time, actually suggested sulfate-reducing cement, and I thought he was crazy, but in the end it was actually quite a good idea. And then we have all these other people helping us. And yeah, there you go. Thank you very much.